Hello. Yeah. Uh, Welcome back, ladies and gentlemen, for the final talk of today's morning session. We are happy to have Professor Fanghua Lin from the Courant Institute, and he will talk about the Polya conjecture up to epsilon-loss and the quantitative estimates for the remainder of Weyl's law. Let's welcome.
Well, thank you very much. Uh, I also wish to express first thanks to organizing and scientific committee to give me an honor to give a talk here, and I'm also very honored to receive this FSA award from ICPS. So today, instead of talk about that this FSA award. Sorry, here almost writes the name. Uh, so I will talk about a work just posted about 10 days ago in archive. Um, but then the title clearly had two parts. First is Polya's conjecture with epsilon-loss. That sounds quite attractive, but actually it just means we are failure to prove it. Uh, 2 months ago, I was very optimistic, and then one constant is not as small as one wish it to be, and then its whole proof collapse, and eventually I say, okay, this is part of life. So one step back, and then get it to epsilon loss version, and then the problem becomes somewhat simpler, but still, uh, you will see today I will talk about sort of they uh, pass over last 20 years thinking about this problem, working along this problem, and how it led to this. And then we, at the time, we think of this quantitative estimate for the remainder of Weyl's law never been made explicit, at least before 2023. And over the last 2 or 3 years, we simply work, don't pay much attention. But actually, over the last couple of years, there are some estimates come out and in very long papers. We read the introduction, don't find the statement, so we continue our work. But eventually, after the preprint posted, this part turns out to be not very new at all. But nevertheless, the approach to that gives certain advantage. And the approach to the epsilon loss version of a Polya conjecture also indicate maybe a possible way to attack this conjecture. It, of all these years, people try to estimate, give a quantitative estimate of involves law, expansion law of the terms. I don't know what particular reason for doing that besides you say, okay, I want to get as high as possible expansion. But one of the bigger problems now solved along this direction, of course, is Polya's conjecture. Maybe they have this in mind, but always epsilon away. So this is the title, and this is recent joint work with Ren Jiang. Uh, so we've been working on for at least very serious over the last 3 years. So here's the theorem. Now, theorem is not very impressive. The Lipschitz, just for convenience, actually is the bounded BB domain. For bounded BB domain, you will see why you assume that, because something tells you it's close to this. A bounded BB domain, then for any epsilon, you can get an epsilon loss version of a Polya conjecture. That is 1 plus epsilon. And before that work, the best estimate is from Li Yao and Blizing, this estimate. And you got basically 2 here. 1 plus 1, 2 here. So this is a little bit of improvement, but still clearly not the whole conjecture epsilon should be 0. But then you have to handle, right? Eigenvalue has to be less than certain number. So epsilon is defined by this number. This is the size of eigenvalue. Now, if bounded PV domain, all these are bounded constant, the volume you can normalize to be 1. It's usual. All these are scaling invariant. And so basically, you have square root of eigenvalue in denominator, logarithm. Unfortunate technical reason you add it, but does not affect this key result. So reduces to calculate first k eigenvalue. Now, this is not necessarily, say, a straightforward, but it's a much sort of simpler problem than many of recently machine-assisted proof, say, of Euler equation blow up or Navier-Stokes equation or other thing. These are fixed dimension and fixed number of k, and it's elliptic, simple elliptic variational problem. And it's in sense that you can parameterize domain, say work on polygon, enough size, and you can work out to see whether or not it's true. So there is somebody in China, actually at the East China Northview, who has been working on this calculation over the last 10 years at least, and calculate up to 35k, k equals 35. Okay, so he stopped there, but he can continue and not more motivate. Find the optimal shape for his eigenvalue. And all the constant come up seems to verify Polya's conjecture with very enough digit to be correct. So it's okay, but the domain shape is not what one usually will expect to say should be convex or something. But no, it goes in like a flower shape, but it's not like a form a cusp. So that is a sort of a background. So the remark is to say for any epsilon you're willing to give up in Polya's conjecture, then for a concrete or for a concrete family of Lipschitz domain or BV domain, this number is uniquely determined, how large the k, and then you have to calculate k's eigenvalue. So this is our message. And point out the two directions. In fact, the original one is basically reduced to whole Polya conjecture to calculate first few eigenvalues. And that just find a little bit of error, little over and large constant, small constant that I mentioned. Now, I mentioned that is actually informed, I think, him very much, Robert Frank, and told us that in 2024 last year and in 2023, the previous year, there are two unpublished work now in press, maybe one of them. This has a part 1 and part 2. In part 1, about 120 pages, and part 2, about 80 pages. You are here. Actually prove what we actually try to prove the remainder uniform estimate. Okay, so the key analytic estimate we use was already there, and we work very hard to it. So on other hand, this going through this tool and led to a bunch of interesting examples for which the Polya conjecture should be true. Okay, so this turns out to be very irregular shape, for example, something else. So there are several more sort of classes of example. But as far as uniform remainder, particularly for second term, involve asymptotic expansion. You just estimate the leading term, then the second term you get a uniform estimate. Even you're willing to give up a little bit of lambda power, that reduces to computational problem. However, that even without reduce, in particular, this paper use very similar approach as we use that actually prove that. Okay, so I sort of a little bit embarrassed after all. Told me that. So that but it's a fun journey. Okay, so this is a message. So now let me tell you, give a little bit of survey, something which did early all along this problem, all sort of connected. And there's a lot of open issues still, as you see, the problem still open. So the story, of course, started with Lawrence's lecture in Codinger 1910. So in which he talked about this Planck radiation formula or semi-field conjecture. Basically, it says the eigenspectral distribution depends only on the volume. This is the physics way of saying. And he even claimed there's no debate hold even in general dimension, multi-connected spaces, and so on. All right. Now, sitting in audience, of course, is to David Hilbert and his blind student, Herman Weyl. So Hilbert was not very optimistic about this conjecture. At the time, he basically say, in lifetime, I will be very happy, if there's some proof in my lifetime. But Herman Weyl gave a proof, at least in dimension 2 and 3, physical dimension. And basically, that conjecture is true. Uh, what is interesting, actually, he didn't use bigger machinery. He uses basically the spectral theory for compact operator developed by Hilbert and his student, sort of a decade before, from 1910 to 1900 to 1910. So now here is Hermann Weyl proved. He proved this. For example, I just take a deletion eigenvalue. So this is so-called counting of the number of case, so that the case eigenvalue is still less than or equal to lambda, less than lambda. And that comes with asymptotic formula. So this is the leading term. And then you have a second term, which, by the way, is a very, very good message. Okay, second term is negative sign, counting. Now, negative sign, unfortunately, has not been used only in some special cases. And so we approach this and manage to use this little bit. That means the next term you have to have a much better control. But at this stage, this should be little o maybe, yeah. Otherwise, it's the same order. So this is little o of this. No. It's large O, yeah. Because this is n minus 1 over 2. This is n over 2 minus 1. So minus 1/2 more. All right. So this is the beginning of the story. And you can check in the cubic case, you're just counting the lattice number. And that is also for Bohr case, the Polya conjecture to be true, actually, you have to counting in very exact way of the lattice point. And for Neumann, a little bit tricky. They have to do also computation. This is the 2023 invention paper by Filanov and others. So for C2 domain, from Weyl's asymptotics, and you get this type of estimate. You have the first two leading term. This is the case eigenvalue has low bound. This is the leading term. And the second term, when omega volume is a fixed area, it's a monotone function of area, boundary area. So this term will become bigger if boundary area become bigger. So eigenvalue actually has better lower bound if you have like a very, very, very terrible boundary. Okay. This is asymptotic formula. That means that is only true for K extremely large. How large? Nobody has an idea. And that is the sort of whole difficulty. Okay. But if otherwise, you will get a Polya conjecture right away. So and that is the message from the Hermann Weyl. Hermann Weyl did it for 2D, 3D, but clearly his method works also in dimension. So now eigenvalue, if you are not familiar with, so this page is just the state of a Polya conjecture. Polya conjecture basically say, you just read from this estimate and you conjecture that. Because for Dirichlet eigenvalue, the case Dirichlet eigenvalue should be larger than a dimensional constant depend on k over volume of omega to the power 2 over n. 2 is the order of differential operator, n is the dimension. In general, it's also true. You can apply to some different order differential operator. So this is a uniform, and so in other words, the second term plays very important role, and then you need to control third term in proper way. Okay, so let's explain what is Polya conjecture and the story about it at the beginning. So let's look at, of course, k equals 1 case, and that is classical Lely-Faber-Klein inequality. So if you give the volume, you minimize the first Dirichlet eigenvalue. Now there's many ways of proving the optimal shape in this case is a ball, and ball is perfectly smooth. Okay, so for first eigenvalue, the shape is perfectly smooth, is along the ball. Now, so naturally, you will look at for case eigenvalue, for domain omega, the volume is fixed, and you try to minimize case Dirichlet eigenvalue. Okay? It's just as a simple. So this is called the shape optimization. So this problem started in early 70s. And the Italian school and some friends involved very deeply with this problem. And the issue is what kind of a class, first of all, at the time, you're going to minimize. So it's an admissible class for which, well, you say eigenvalues are defined. So it turns out you will see it's so-called a quasi-open set. And then, because the problem is always on whole Euclidean space, and that is the usual problem of concentration, compactness, and splitting. You could split domain in two, and so on. For example, for k equals 2, what is the optimal shape? And it's very easy to prove is two equal balls. You can put close tangent to each other or put far apart. It is this one. Why? Because the nodal domain for second eigenfunction had to have two nodal domain, had to change in sign, second eigenfunction. So each one you can take away, and each one has a volume, and each one you symmetrize to get is basically two ball. And then you compare, you add these two eigenvalues together, or say because they have the same eigenvalue at the beginning, and you just say, well, okay, it's one of the, because minimizing one of the largest ball, and then you will find that these two balls have to be equal size. And so have to be equal size two balls. But then you already see the problem is in calculus variation, you can put a ball in any position. So you have to allow this kind of phenomena. Then you have to do certain surgery in minimizing sequence or do minimizer. You allow to have a multi-connected region in general. And so you may ask a question, if a k is large, whether or not very well spread. So the computation tells you occasionally spread. Most time won't. Okay, so, but anyway, in any cases, it's like in many calculus variation problem, in PDE or calculus variation of geometry variational problem, that you need to handle infinite stretching, very thin long regions, a little bit connected could be, or it's just splitting. Right? One is sort of like a vanishing, the other called splitting, dichotomy, this situation. Now, so these are not story. These are not our result. It's due to many people. So it's well recorded in Henlon's book on this extreme problem for eigenvalues of Laplacian. So There is a convex region that solve the minimizing problem. Among convex region, you can minimize. Okay, you fix volume among convex region for case eigenvalue, you try to minimize. What could happen to convex region? A convex region, basically, if your volume fixed, essentially is compact. The only thing become not compact is the region collapses. One of the direction become very caught in two parallel plane, which small distance collapse. But then you will see the eigenvalue have to go to infinity. So whenever you fix k, you can show that kind of situation will never happen because you can easily compare with a rectangle which containing is just one direction that kills the problem already. So for convex region, you have. But now the issue is, of course, in this case, you also want to know exactly how small that one direction can get to be. And that is another thing, large constant, small constant, that issue that we made earlier a little bit of mistake there as well, but related. So in general, there's a bounded, it's always bounded, a quasi-open set of finite parameter. So that is an Italian school after many, many years, that's around the 2010, 2013, that period, they eventually prove that result, which is useful. But of course, what is bound, what is finite parameter, uh, you know, there it's large constant, small constant issue still will be there. Okay, so in this award paper, we did discuss some general principle. So first of all, there's a multi-connected region which realizes the minimizer. Okay, very first. In fact, it's an open region. Okay, so quasi-open is indeed open. And not only that, if you start to have a string, say k, you can think of k is most indices, k's eigenvalue indices like a k. And you split it into k1, k2, km region, and most indices add up, and the volume add up. So you will have this, but the eigenvalue will certify such inequality. Now, those two actually is possibly most interesting or a hard case, you believe or not. M larger, slightly better. And that is like in Li Yao estimate. The coefficient there in counting function is m plus 2 over n. When n dimension go to infinity, almost like go to 1. So that is, at least for counting function, is almost optimal. But you have this. Now, when n larger than 2, if you take 2 over n power, both sides, the eigenvalue, the other side becomes sublinear growth. Now, sublinear growth is something I always love. Okay, so the early work for Fajev and the Scrum knot solution, where we prove giving hope index, and you look at the energy, and energy and hope index, the relation is energy equals hope index absolute value to the power 3 over 4 in 3D. And you can look at the general dimension and higher dimensional version as sublinear. Now, recently, Anton Wasson and others give a proof of use another open problem. You say in any compact smooth remaining manifold of dimension, say not larger than or equal to 7, then you will have infinite many minimum hypersurfaces and basically smooth. Yeah, also. So there one use minimax method. Minimax method. So you control the index as well there. Okay. And what is important there is, believe it or not, is very large estimate of Gromov that in terms of the p is the number of parameters in minimax, the index, and it's a p to the power n over n plus 1. And it's a sublinear. And sublinear, that means you exist minimizer in this class, minimax, sort of like a generalized minimum. Not only that, you cannot infinitely split. So what happens if you only have a finite number of the surfaces, then the index will be supported in one of the surfaces compatible with P. But then each one is stable, so that means you have a P sheet. And then the area growth will be linear in P instead of sublinear. So this type of idea is being very useful. And to explore here, it's become a little bit tricky. But so therefore, n equals 2 is very interesting situation. And you just look at it. Now k to the power 2 over n become like a k. And you basically want to say Polya conjecture will be true because the worst scenario is true. You minimize among k's eigenvalue among domains with a fixed volume, and you got this minimum number already larger than this dimensional constant in Polya conjecture. If you can prove that, then it's all done. Okay, so that is earlier. So there's a strong splitting argument, but that is for minimizing sequence, very similar. It's in other words, not only true for minimizer. Before you go to minimizer, you already can do a little bit of surgery, keep a similar inequality. So the main theorem, which says that because of sublinear growth and some other fact, that in fact the region for minimizer is M connected. M is always much smaller than K, much smaller than K. Okay, now you will see this result is consistent with the earlier in 1960s. I think he was a postdoctor of Hermann Weyl. He did this at the IAS. I will mention that. It's connected. It's basically say K's eigenfunction. You have a new K nodal domain. How large new K can be? Okay, K's eigenfunction, you have a new K eigendomain. You can have just a 2, but how large it can be? Now, Coulomb theorem, you use minimax, at most is K. That we know. Okay, but this is the first sort of quantitative estimate. But there's a theorem which says that will be strictly listing a portion of K. Okay, so this is connected. So this we awarded very honored to award this FSA. This is only a theta product, but I did with Klim Vitasov at the time. He was postdoc at the Coulomb between, I don't know, 2015 and 2018. So we wrote these two papers together, published both in CPAN. Now, this problem here to be degenerate. For degenerate case, we don't get the smoothness very good. In other words, you may have a cusp domain. Okay, certain calculation indicate after it's not convex, go in. But really cusp, we really don't see, but it's cusp when K is large. But for, say, the functional, Liao and Blizin consider, say, average of eigenvalues, that you got a perfectly smooth. Now, we just prove in lower dimension. Dimension actually less than or equal to 4. It's perfectly okay. But I believe it's true even for higher dimension. Why? The basic sort of intuition behind it, if I tell you that all theorem is trivial, is the first eigenvalue, if functional involve first eigenvalue, say some small number times first eigenvalue, if it's there with less of the eigenvalue, higher eigenvalue involved certain fixed functional, if you minimize that, the function is monotone in each variable across the values. So become an elliptic problem. So if you have this, the solution will be smooth in some way. Why? Well, the reason is if all the case if you consider boundary point, if all the case eigenfunctions vanish exactly first order there as well, then naturally free bounded thing tells you will be smooth there. If you have a high order vanishing, that is where the cusp might be possible at the boundary. But when high order vanishing, when you blow up, you only see first eigenfunction. First eigenfunction always linear near the boundary. Vanish at the boundary, but the linear grows. So that means the first eigenfunction will you always see, and that is like a strongly elliptic, and therefore it's smooth at least in low dimension. Now this proof does not help you for Polya conjecture. Just certain description of what kind of a worst type of domain can have, a much refined regularity and so on. But sometimes it's interesting. It does not help you for Polya conjecture. But this idea of proving that is become idea of proving certain free boundary regularity with Bernoulli type general, because it can be very general, Bernoulli type boundary condition. And the function can change in sign. Now before, the most known classical theory of capillary, either one phase or two phase, you have to have a clearly changing sign at the free boundary. Okay, particularly one phase, just not negative. So one sign. For one sign, the problem should all go to capillary, where he contributed all the key ideas there. And that one can establish free boundary. And higher dimension maybe have partial regularity. But for changing, the story is very different and very complicated. And this is the paper actually dealing with also changing sign. So we have free boundary condition changing sign. We did this, actually it's not something we initially intend, but turns out over the last 5 years or 2 years, there's quite a few papers now dealing with these things and analyzing further. So actually it has more interest in free boundary regularity issue than the original problem we intend. Okay, so this is part of the story. Now, let me tell you about 20 years ago, the first problem I started with capillary. That is also optimal shape. And this I told Ilya Lieber and made a certain conjecture. He said if you can prove something like that, it will solve a lot of the problem in statistical physics. Very hard problem. So, but this is an interesting problem. But you can see that it's connected. So what is the problem? The problem is easy to describe. Give you any bounded domain, you can assume smooth, does not play much role. Domain in Rn. You try to divide into n parts and mutually disjoint subset. How you divide, what kind of set alone at the moment, nothing is clear. Say, from our previous knowledge of the problem, that means you require certain quasi-open sets. Okay, but that's all. Quasi-open just means different from open set by arbitrary small capacity. So that can be terrible in many ways. Right? Coordination to set, you can add and subtract anything. You try to minimize each domain. You have M domain. You have the first deletion eigenvalue. All these are deletion eigenvalue. Deletion. And you try to minimize the sum of the first deletion eigenvalue. You try to minimize that. And the question is, do you have a minimizer? What a minimizer looks like? So you will form a domain, and domain will have interface, will have a junction as well. Okay, so this is a typical free boundary, but how you formulate it? And what kind of a set, again, you try to minimize, say quasi-open, and then you have to do variation. So actually we're changing this problem completely. We just say this problem equivalent to certain harmonic mapping problem to a tree that is with n branch and say n coordinate, positive coordinate axis. And map to this. And harmonic map problem because target, even though is singular, the good thing is contractible. Just in say 3 axes is contractible, or 3 surfaces like this corner of a wall. It's all contractible, very nice, and there will be no bubbling in harmonic map. But it could be, say, 3 could be positively curved. But 3 line turns out is non-positive. You define distance proper. So these are singular spaces. In general, Alexandrov spaces. Singular spaces with non-positive curvature. Now the dimension is 1, but it's a large number of branch n. So we do that, and we prove minimizer exists. And this minimizer, each component, each branch corresponding to a nodal domain, okay, where the support is 1 branch. And with give a natural partition. And with is optimal. The 2 problem equivalent, same minimum value. From harmonic map theory, there we have a lot of tools, in particular, unbranched monotonicity and vanishing order control, so on and so forth, unique continuation. And there we led to essentially all the junction, in this case, all the interface are piecewise are smooth C1R and with junction say, points. The junction point in large dimension is in -2. Co-dimension 2 junction. So in 2D, it's just like this points, a finite number of points, bounded number of points. So you have this. And the further result by Deleuze and my former student followed Deleuze's work for general multivariate harmonic function. But follow his idea, he proved this co-dimension 2 measure is also finite, means rectifiable and with a finite measure. So that being a lot of them, and Luis Caprari and I also consider its gradient flow, and we managed to establish exactly same version, parabolic version. The rectifiability stuff is proved in my another student thesis of 2008, but that was 2014. So that was done. Okay, so the work we have 2 key work there. The main idea 2008 is about the eigenvalue partition problem, and 2010 is more general, both divergent and non-divergent, but published in James. Very short paper, too. Both are very short paper. We proved that result. Why consider this? You see the connection already. You notice actually these partition and M's eigenfunction are closely related. So even though M's eigenfunction may not have exactly M nodal domain, but you may have M chunk of a mass. Okay, so there's a lot of conjecture you can make. You maybe certain chunk of the mass is still there. In other words, not consider just a 0 set, but near 0 set, near critical value set, etc. But this alone all has a lot of issues. Let me give a little bit of summary. So we basically have these 2 particular problems I discussed here, but there's a lot other problem one can do. Existence, regularity minimizer, uniform estimate, and that one, particularly as k go to infinity, still issue there, and that is welcome some young people, expert here, to look into that. From harmonic map, there are certain issue. From the usual domain thing, there are certain issue, but I miss just by little o or large o. So that is unfortunate. So therefore, we step back to all the story of the last 3 years. Nodal partition. So if you have eigenfunction, that automatically give domain a partition in terms of a nodal domain, and that called the nodal partition. Now, as I said, the number of nodal domain is interesting, and the Coulomb theorem says the number of nodal domain is always less than k, k's eigenfunction. Okay, by classical minimax. Now here's the thing which I'm referring to. By the name, I'm not sure I can say properly, the Plagial theorem, which says the number of the nodal domain for k's eigenfunction over k will be strictly less than 1. There's a number you can estimate using Bezo's first zero and the dimension calculation in 2D. Even I can do the computation, find out, yeah. So it's this number, clearly. Take off the further digit, it's 4 over 2.2 square, so it's clearly less than 1 in 2 dimensions, but works in arbitrary n dimension. Now, proved by this way, it's sort of very naive, right? So how do you prove? If you have a new k nodal domain, one of the nodal domain volume has to be less than total volume divided through by uk, and then by symmetralization, it tells you the eigenvalue has to be so and so. And from there, you get k's eigenvalue. But on the other hand, Weyl's asymptotic law tell you something else. So you compare both, you will find this new k has to be less than this number. It's so rough estimate. But in order to prove that, now look at Bourgain's paper. It's not very long, but it's very difficult to read. He improved this constant just tiny little bit. That is a very good problem. What is exact this ratio? You get a better. Honestly, I don't know why Bourgain look at this, but Bourgain, in all kind of problems, but he must have a motivation, which I don't know. But he improved this constant just a little bit. I welcome you also to look at Bourgain's paper. So Capellari and I eventually did all the free boundary regularity, established junction, and junction said we have Weyl discretion and flow, etc. But then just in 2D, because 2D, if you cannot understand, because 2D lattice is simple, yeah? 2D lattice is relatively manageable to visualize. And in 2D, first of all, what is this? This is sum of the first eigenvalue in m partition. Say, give me any open set, bounded open set omega. I divide through into m parts. Okay, and calculate the first eigenvalue of each part, sum together, divided through by m squared. Well, divided through by m is natural, but m squared is because each one volume like 1 over m. And the Weyl asymptotics in 2D tells you exactly this number. So the 2 is 1 plus 2 over n, n is dimension. So it's 2. And if you normalize that, so we conjecture that the limit exists, and the second, this limit has to be hexagon. What this means, if you take a more and more partition number, you look at the domain inside, boundary will be affected, a little bit deformed. But if you look at it inside, most parts, it will form a lattice packing because it had to form a packing. Now you will think each, well, divided in n part, optimal one for each part is ball. But a ball, if you pack ball, you have a lot of space left over. Clearly, it's not good packing. So you have a triangle packing. Regular triangle is the best one because the smallest eigenvalue. It's proved. You can have a square or rectangle packing. Rectangle packing, well, among all the rectangles, square is the best possible. We say more, the first eigenvalue reach minimum. So you have a square packing, and hexagon cannot form packing. And the next one is the hexagon. Now, the larger the size, regular polygon, the smaller the eigenvalue. As the size goes to infinity, it becomes a circle. And circle is by symmetralization is the smallest eigenvalue. But you require to form a packing, and you want size as large as possible, is the hexagon. So when I talk this, almost 10 years ago in front of Eli Lieber. And he said, yes, it's nice conjecture, but how can you prove anything like that? I say, you know, what else can be? So if you cannot find a counterexample, this is the proof. Okay, no, I'm joking, but it's not the proof, but you cannot imagine anything not this. Okay, so this is a conjecture. But the first thing, what we proved, actually, it is indeed true. Uh, this sum and take limit, it has a unique limit. And then not only true, it is also true in higher dimension. So this is the shift here. Or in any higher dimension will be this one. Yeah, this one. And where does m go to infinity? Independent shape of a region, independent whatever open set you start with, this limit will give you always a unique number depending only on dimension, not depending on shape you start with, so long as you go to m go to infinity. So this actually gives you an ecology in positive direction for the Polya. So the conjecture of this one remains open. I don't know that can handle something like that. Okay, now let me return to this thing. So even though now this group is here, much more than I do, but that is how at the time we did early papers, basically anything before 2023, and when we see the paper by Filanov, we kind of nervous. We say, oh, okay, it's just for ball. We are still safe. And the method is a classical counting of the lattice point. So we are in safe zone. So the issue is to say, well, in order to prove Weyl's law, since the early attempt all stuck somewhere, so let's consider this remainder in Weyl's law. If you can get a very nice estimate instead of asymptotic and not computable. So the best estimate for piecewise smooth region, Seeley has very nice argument. It depends on, for next term, depending on the so-called periodic geodesic, certain quantum ergodicity. Periodic geodesic has a measure 0. But if you don't know, I even don't know what exactly it means, but it's related to quantum ergodicity, then you have some control on the certainty. So this one, and so, it's survey paper every talking about all the history and so on. So for our Polya conjecture, Polya proved that for domain tail, this argument works also in higher dimension. Now, really the first sort of non-trivial breakthrough is due to Lipton. He basically showed all product domain, so long as the first factor, right? First factor in one is dimension larger than 2. Polya conjecture is true. Then this product region Polya conjecture is true. Very nice argument. Then another one is Filanov and all, but they not only verify for the ball, but if you check that, is also for circular annular region, right? Circular annular region, say in 2D, or and then for certain sector of the sphere, they also prove that. Now, I mentioned several times already that Li Yao and Blizin estimate. The great thing about this is independent on what type of domain, you essentially no assumption, just a volume. Volume, this number, which if you can get a 1, right? If you can bound below by 1, then you solve the Polya conjecture. But this number, you notice that it's larger than or equal to. If you take the other way, if you look at the Polya conjecture in other way, and then with the number here, what we want to show now is 1 plus epsilon, but that number is 2. But the good thing is independent of anything. Okay, it's a beautiful proof. And afterwards, some of us probably know there are many long proofs try to generalize that. But yeah, so it's just a very nice proof. It's almost legit. It's very hard to make a substantial improvement from that. Yeah. Now, epsilon loss aversion is clearly we failed our early attempt. So we step back. Okay. Yeah, step back. And so for any epsilon fixed, we want to prove Polya's conjecture was here replaced by 1 plus epsilon. So better thing now this involve the low order uh, Weyl remainder is to quantify. Uh, our approach is try to quantify, but with quantification. They use Coulomb Hilbert actually improve Coulomb's original argument is use Dirichlet-Neumann bracket, and from this estimate, I will compare all these at the end slides. And then, of course, laptop and then from laptop, I will measure at the end, improve this to a more precise. The earlier dependence is say just like in most of PD, just depend on omega will be sufficient. So our proof is it's first to get 1D, the least mean improvement, very inspired by this laptop's argument. Then what we do is instead of looking at counting from lower bound for omega, we look at it, suppose it contained in some bounded Q. Look at its complement and to calculate counting function of its complement upper bound. Now, counting function upper bound by minimax is much easier. You can even ignore all the boundary terms. And this is an advantage, and this is one of the difficulty to get a quantitative estimate in Coulomb Hilbert. So we look at complement to get upper bound of its complement counting function. So therefore, uh, therefore you will have lower bound from counting function of omega. And the lower bound of a counting function of omega will give you upper bound of eigenvalue. So it's all twisted in this way. So now let me review after Robert told me recent progress. I check again Coulomb Hilbert, and Homeda. So they first get such estimate, constant dependent dimension and omega, and uses so-called the Dirichlet-Neumann bracket. So this is the size of omega and so on. And then actually in that paper, they use follow, but they actually in Coulomb Hilbert, and then they get this number can be sort of calculated. For example, if you know it's a BB bounded domain, this number will be very clear. So Coulomb Hilbert is basically from inside domain give a decomposition, disjoint decomposition by cubes, and then you look at the counting function, and then you have the counting function upper bound. But that you want to make the difference, calculate its difference. Instead of this difference, you look at this difference. And that is exactly Coulomb Hilbert, the Neumann Dirichlet. This n corresponding to Neumann. But then there's the remainder term. Now, so Frank is here, so I'm nervous to talk about that. But they managed to get this estimate also very precisely. So involve two constants here. And the first constant they get is this one. And the second constant, they also get this one. So the boundary term also handled. Always give up a logarithm factor, which is magic, right? And only when you work on this, you realize you have to give up something. So at least for now. But for certain domain, actually, you can do without giving up. Large class we have. So we found that there is a very weird looking to very irregular and you think it's worse for Polya, but actually it's true. You can say it's for technical reason, it's true. So, okay. So I talk about all proof, also use this with some modification, but just from it's this lower estimate. Both upper is easy, but the lower estimate for this counting function for the Q, and then verify Polya conjecture. But uniform third term estimate, as I said, very well reduce whole Polya conjecture to computing problem. I think this I talk enough, and thank you.
Thank you for the wonderful talk. Are there any questions in the audience? Yes. Yes.
And you mentioned this smoothness for result for the optimization.
Yes.
For the partial sum, you say you get smoothness of the bound. Do you get the correct length? I mean, can you see that
it's very easy to get before you're scaling. Very easy to get say in 2D constant, large constant times square lambda sort of thing. But you want a tiny constant times square lambda that require something else. So that is the first thing we miss at this stage. I still believe there's maybe square lambda over log lambda. There's a factor you probably can squeeze it. But since I didn't work out all the details, but so I cannot say that. But it's still hopeful there. But of course, if you can get a uniform, independent K, then the whole problem solved. Yeah, whole problem solved. So you see that life is interesting, right? This way. In front of Professor Yo, I cannot talk about, say, or Professor Chang. I cannot talk about, say, my age. At my age, just for fun, of course, yeah. Waste some time, it's okay, even though not much time you can waste, but it's okay. It's a lot of fun being work on that. But you can see I worked around this for many years before I sort of have encouraged over the last 3 years working with Jean to exactly look into the polya. We excited for a couple of months, but when we really write down and we find a little gap there. And so that tell the whole proof collapse. It's not surprising, but we will say, okay, so desperate, we have to looking for something else. So got this epsilon version reduced to a computational problem. But I think one should work a little bit hard to get reduce whole Polya conjecture to a computational problem at least, like in Weyl case. That the computational problem is still large task, but it's much more easily doable and verifiable by computer these days. And with supercomputer power, you just need so somebody at East China normal view with just laptop computer already able to calculate 35K up to 35. I think one can sort of combine. Yeah, it's not going to be sort of machine assessed proof. Yeah, you just print out the digit, you can calculate at least in 2 or 3 dimensions. But optimal shape is not convex at the beginning. Was surprised, but think about a little bit. It's always curved in a little bit. Start with third eigenvalue. Yeah. So.
Are there any more questions in the audience? Okay, let's thank the speaker once again for the wonderful talk.